Hello everyone. Today our group will be presenting Portfolio Optimization Part 3. In this project, we use Python financial market data in Tableau to build and analyze a generalized portfolio optimization model. Throughout the presentation, we will discuss our methodology, explain key statistical and financial concepts, and interpret the results of our portfolio simulations. For Portfolio Optimization Part 3, we built a generalized portfolio simulation engine. Unlike Portfolio Optimization Part 2, which used a fixed list of stocks, this program allows a user to enter any set of ticker symbols in any date range. The program then automatically downloads market data, computes portfolio metrics, simulates 10,000 portfolios, generates visualizations, and exports all results into Excel. The objective was not only to automate portfolio analysis, but also to evaluate how different combinations of stocks impact expected return, risk, and risk-adjusted performance. By creating a flexible system, the model can be applied to virtually any investment portfolio instead of being limited to a specific set of securities. This project required several technologies working together. Python served as a primary analytical tool. It collected stock data from Yahoo Finance, imported risk-free rates and market risk premiums from the Kenneth R. French data library, calculated portfolio statistics, and simulated 10,000 random portfolios. ChatGPT assisted with developing and troubleshooting portions of the Python code, allowing us to automate much of the analysis while still validating the results ourselves. The outputs were then exported into Excel and imported into Tableau, where we created visualizations that made the results easier to analyze and communicate. By combining these tools, we were able to build a complete portfolio analytics workflow similar to what might be used in a professional investment environment. Several statistical concepts were essential to this project. First, standard deviation was used to measure portfolio volatility. Across the 10,000 simulated portfolios, standard deviations ranged roughly between 3.8% and 5.8%, showing that different combinations of stocks can create very different levels of risk. Covariance and correlation were also important because they explain how securities move relative to one another. Diversification works when assets are not perfectly correlated, which helps reduce portfolio risk. Finally, regression analysis was used to estimate beta. Portfolio excess returns were regressed against the market risk premium to measure each portfolio's sensitivity to market movements. Together, these statistical tools allowed us to evaluate both total risk and market risk for every portfolio in the simulation. This project also applied several important financial concepts used in portfolio management. Expected excess return measures the return earned above the risk-free rate and represents the reward investors receive for taking risk. Beta measures systematic risk or exposure to overall market movements. To evaluate performance, we use both the Sharpe ratio and the Trainer ratio. The Sharpe ratio measures excess return relative to total risk, while the Trainer ratio measures excess return relative to market risk. Our highest Sharpe portfolio, Portfolio 8986, achieved a Sharpe ratio of approximately 0.230. The highest Trainer portfolio, Portfolio 5850, achieved a Trainer ratio of approximately 0.015. These metrics allowed us to identify portfolios that deliver the strongest risk-adjusted returns rather than simply the highest raw returns. This scatter plot compares expected excess return to portfolio standard deviation. Each point represents one of the 10,000 simulated portfolios. The upward sloping pattern clearly illustrates the risk-return trade-off. Portfolios with higher expected returns generally required investors to accept higher levels of total risk. The highlighted portfolio represents Portfolio 8986, which achieved the highest Sharpe ratio in the simulation. This portfolio generated an expected excess return of approximately 0.91% per month while maintaining a relatively low standard deviation of about 3.95%. The reason it stands out is because it provided the best balance between return and volatility among all portfolios tested. For a diverse investor concerned with total portfolio risk, this would be one of the most attractive portfolios in the simulation. This visualization compares expected excess return to beta. While the previous graph focused on total risk, this graph focuses only on systematic market risk. The highlighted point represents Portfolio 5850, which achieved the highest Trainer ratio. This portfolio generally generated an expected excess return of approximately 0.78% per month while maintaining a beta of roughly 0.51, significantly lower than many other portfolios in the simulation. Because the portfolio achieved relatively strong returns while limiting market exposure, it delivered the highest reward per unit of systematic risk. This type of portfolio would be particularly appealing to investors who are focused on controlling market exposure. This visualization compares the Sharpe ratio and Treynor ratio for all 10,000 portfolios. One of the first things we notice is the strong positive relationship between the two measures. In general, portfolios that perform well under one metric tend to perform well under the other. However, the relationship is not perfect. Portfolio 8986 produced the highest Sharpe ratio, while Portfolio 5850 produced the highest Treynor ratio. This difference occurs because the Sharpe ratio penalizes total volatility, whereas the Treynor ratio only considers market risk. The visualization highlights that investors may reach different conclusions depending on which type of risk they consider most important. This chart compares the stock allocations of the two highest performing portfolios. Although both portfolios ranked at the top of the simulation, their weight distributions are noticeably different. Portfolio 8986 allocated larger weights to stocks that improved overall diversification and reduced volatility. Portfolio 5850 allocated more weight towards stocks that improved market risk adjusted performance. This comparison demonstrates that portfolio construction matters just as much as stock selection. Two portfolios can contain the same securities but produce very different results depending on how the weights are assigned. To conclude, Portfolio Optimization Part 3 demonstrated how technology, statistical analysis, and financial theory can be combined to evaluate investment portfolios. Using Python, we simulated 10,000 portfolios and measured performance using expected excess return, standard deviation, beta, Sharpe ratio, and Treynor ratio. Our analysis showed that Portfolio 8986 delivered the strongest return relative to total risk, while Portfolio 5850 delivered the strongest return relative to market risk. The Tableau visualizations clearly illustrated the relationship between risk and return and highlighted how different risk measures can lead to different portfolio choices. The key takeaway is that there is no universally perfect portfolio. The best portfolio depends on an investor's objectives, risk tolerance, and definition of risk. Effective portfolio management is ultimately about finding the risk-return trade-off that best fits the investor's needs. Thank you for listening.